uh, introduce the next speaker. It's Nawaf Nazir. Nawaf, you're here, right? Yes. Let me give a bio. Nawaf is a student member of IEEE, and he received master degree in electrical engineering from Virginia Tech in 2015. He's currently working towards a PhD degree in electrical engineering at the Department of Electrical and Biomedical Engineering at the University of Vermont. His research interests include modeling and optimization of virtual batteries in power systems. I think Nawaf is working with Max Almassalkhi, if I'm not wrong. And he's gonna talk now about stochastic multi-period optimal dispatch of energy storage in unbalanced distribution feeders. Well, Nawaf, stage is yours. And please keep 15 minutes in mind and don't exceed that. Thank you.
All right. Thank you, Professor Jalal. Can you see my screen?
Yes, I can. And also I hear your voice very clearly.
All right. Sounds good. So my name is Nawaf. I'm a PhD student at the University of Vermont, and this is my work with my advisor, Professor Max Almassalkhi. The topic of this presentation is stochastic multi-period optimal dispatch of energy storage in unbalanced distribution feeders. In this work, we look at how we can dispatch energy storage in unbalanced distribution feeders to counter the variation in renewable generation. So first, let me provide some motivation for our work. So with the increasing penetration of renewable energy, such as solar and wind, there is increased variability in generation. Also, with more and more distributed generation, these distributed resources are supposed to participate in ISO market opportunities. So because of these challenges, it is important to look at the role flexibility can provide when we have a lot of renewable generation. So load flexibility can provide value through peak demand reductions. And there is a lot of potential of load flexibility in the US, estimated to be around 200 gigawatts in the US by 2030. Furthermore, the battery capital costs are predicted to rapidly decrease in the coming years. So all of these points highlight the importance of using energy storage when we have a lot of renewable energy penetration. So the challenge is the uncertainty in the forecast. So this figure here shows the 10-second resolution of solar power output, showing the highly variable nature of solar generation in the intra-hour time frame. So lately there has been a lot of work in the intra-hour solar forecasts, and a lot of these methods are now available. And using these forecasting techniques, we can actually predict how the error in the forecast grows over the prediction horizon. Like in the example I'm showing here, I'm updating the forecast every 30 minutes, which is a reasonable technique. Many providers of forecasting tools do that. So based on that, the figure at the bottom shows the region of solar uncertainty corresponding to that forecast. So the question that we're asking here is, what role does the grid or the network play in all of this? So we have these bunch of distributed energy resources that are distributed over a network. So as of now, today, the distribution operations is basically a volt-var focused operation where we use transformers and cap banks, usually 10 to 100 in number, to control the voltage in a distribution network. And these are mostly set manually. But with extreme solar PV penetration and more smart inverters and the need to provide dynamic energy services, now we have a lot of controllable resources, tens of thousands of smart devices. So what that does is it increases the complexity by more than a factor of 100. So the need is that we need to contain this complexity through optimization algorithms that can handle this. But the problem is that we have this three-phase AC network, and also then the energy limits also make this problem very complicated. So based on these challenges, the objective of this work is to make the best use of the available energy resources to meet dynamic market opportunities while accounting for the AC physics of the network and the uncertainty of solar PV. So in this slide, I'll just highlight what are the challenges that we encounter when solving three-phase multi-period OPF. So we have a distribution network, and in this case, we have distributed energy resources, or DERs. We have solar PV, and then we have a three-phase grid. So the power flow equations that relate the variables in a three-phase grid are nonlinear, so which makes the optimization problem non-convex. There has been work in literature, such as in 4, 5, and 6, that deal with this non-convexity using some kind of relaxation, such as SDP, SOCP, or some kind of linearization techniques. But the issue is that these relaxations often fail under certain circumstances. So there's no guarantees that they will hold. For energy storage, 7 has used a multi-period SDP relaxation, whereas 8 uses an ACQP with an SOCP relaxation. Again, the issue here is the non-convexity of the power flow equations. Furthermore, when you have multiple time steps, that increases the problem size substantially, leading to a large increase in solve time. And finally, to deal with the uncertainty, 9 has developed a chance constraint formulation that basically converts the infinite dimensional stochastic optimization problem into a finite dimensional deterministic one. 10 uses a scenario-based approach, whereas 11 converts the ACOPF, stochastic ACOPF, into an STP formulation. All of these works make some kind of assumptions on the network by which they are able to convert this stochastic problem into a scalable formulation. In this work, what we want to do is that we want to avoid making any of these modeling simplifications. So we want to solve the full three-phase multi-period stochastic ACOPF, but still be able to provide some kind of a scalable solution and some kind of feasibility guarantees with some probability index. Let me just briefly go over the physics of the three-phase power flow so we can derive our model. So assume we have this three-phase line. So in this line, you can apply Kirchhoff's voltage law to get the relationship between the voltages and the currents shown over here, which I can also write in matrix form like this. What I can do is I can multiply both sides by their Hermitian, so I get this equation, and then I can use this transformation by introducing these new variables W, S, and L, and I get a linear relation between W, S, and L shown here. And then the only other equation is the constraint which relates these transformed variables with the original voltages and currents. I can also write this in terms of these three nonlinear equations here. So this represents the nonlinearity in our model. And this matrix equation can further, this has been done in the literature, can be represented by a positive semi-definite constraint and also a rank constraint. So what we want to do is we want to get a convex formulation of this problem. So we want to relax the non-convex constraint. So what we do is we get rid of the rank constraint, which is the non-convex part. And then we just keep the positive semi-definite constraint. So we now have an STP problem to solve. But still STPs are numerically, they're not so robust. So what we do is we further do another relaxation and we get these three second order conic relaxations. So SOCPs are generally more numerically robust. Further, you can solve them at a faster time scale. So we're going to use SOCPs. So you can think of this relaxation as if you have this nonlinear set or non-convex set, what we do is we relax to get a convex relaxed set. And then what we want is at optimality to somehow push our optimal solution towards the feasible set so that we get a zero duality gap and our predicted solution matches the actual physical one. All right, so using this relaxed SOCP model that we developed in this slide, I will show how we dispatch these flexible resources in the deterministic case. So in this case, I assume that the forecasts that we have are 100% accurate. So we have this relaxed SOCP model shown in 1. Based on some objective, we solve this problem. And then the solution that we get, we use that to solve a decoupled nonlinear program, DNLP I call here. So, but what I do is I fix the active power set points shown in 2. So because of that, what happens is when you fix the active power set points, I fix the state of charge. So as a result, the different time steps are now decoupled and you can solve them independently and in parallel. So what I do is based on the SOCP solution, I fix the active power set points, it leads to decoupling of the time steps, and then I solve the decoupled NLP or DNLP shown in 3. So this way I'm able to get a feasible solution from the NLP, and also the solve time is not increased that much because I can solve them in parallel. So this is further illustrated by this figure here, which shows what the values of the reactive power I can choose depending upon the solution that I get from the SOCP. So I get some real active power solution from the SOCP. Based on that, I can calculate the set shown in blue over which the reactive power can vary. So then the NLP has to basically choose some reactive power in that range. right? So then I also can get a relationship between the optimal values of the SOCP, the NLP, and the decoupled NLP. Even though we don't solve the NLP, but we can get this relationship. And based on that, I can get an upper bound on the optimality gap that we obtain in this case. So when we solve this NLP, not only do we have a feasible solution, but we also have a guarantee that our optimality gap will be within some range. So using this SOCP NLP coupled approach, we are able to turn a hard non-convex problem into a scalable solution. We can optimally dispatch batteries over multiple time steps while also adhering to three-phase AC physics. And for further details, you can check out our paper in Transactions for this, more details on this. All right, so what about when the forecasts are uncertain? So in this case, what we do is we augment our deterministic formulations with chance constraint. So based on the optimal solution that we get from solving the SOCP NLP coupled problem, what we do is we linearize our model around that point to get a linearized model, and we get the sensitivity factors, which shown here by gamma, which basically relate the constrained variables with the control inputs. So then based on this linearized model and the model of uncertainty, which we assume for the forecast errors, we robustify our model by getting these bounds, updated bounds on our constraints. In this case, I'm showing the updated bounds for the voltage constraints, VB upper bar and VB lower bar. So then in the next time step, then we solve our SOCP NLP coupled problem based on these updated updated constraint bounds. And then, so the process repeats. And then finally, we validate our results by solving an AC load flow based on the actual demand and solar PV. All right, so in this slide, I will just mathematically formulate the chance constraint problem and how we use that chance constraint formulation to obtain these tighter bounds. So consider a constrained variable y. This could be like voltage or branch flow, and also a random variable omega, which could be the error in solar forecast. So then I can obtain the sensitivity factors of y with respect to omega, called here gamma y, assuming that omega is zero mean. And I can, based on this now, I can express y as a linear function of omega. So now that I have this linear approximation, what I can do is I can express the following stochastic constraints. So now I have these two stochastic constraints. The probability of y plus gamma y omega less than or equal to y max has to be greater than 1 minus alpha y, where alpha y is some acceptable probability of violation that I can choose. So now this linear dependence enables the use of an analytical chance constraint reformulation that can be utilized to obtain these tighter bounds shown here. So now I obtain these bounds where y is less than or equal to y max minus phi inverse 1 minus alpha y times the 2 norm of gamma y times sigma raised to power 1 by 2, which I call as yb upper bar, and similarly I obtain yb lower bar. So these yb upper bar and yb lower bar are the updated or the tighter bounds for the constraints. And this phi inverse 1 minus alpha y, this is the safety factor, which depends upon the assumption that we make on the distribution of the forecast error, whether we model it as a Gaussian or some other kind of distribution. Right, so that brings us to the nature of the uncertainty. How do we model the uncertainty? So if we look at the forecast errors, we assume them to be a uniform unimodal distribution, which is a reasonable assumption to make. However, so the Gaussian safety factor cannot be used here as it cannot guarantee performance. We can use a Chebyshev approximation, and that will guarantee performance for a given mean and covariance, but it's very conservative. Instead, what we do is we use a unimodal Chebyshev approximation, which is less conservative, as we use the additional information of having a unimodal distribution. And then we can approximate the safety factor for the unimodal Chebyshev given by this expression, which has been validated in literature. And we can also see how the safety factor changes depending upon what kind of distribution we use. So for Chebyshev, we see that the solution is very conservative. It is less conservative for Gaussian, whereas unimodal Chebyshev is somewhere in between. All right, so now using all these tools that we have developed, what we want to do is we want to see how the solar forecast of uncertainty grows. So here I'm showing, based on the forecasting models that we have, how the error in the forecast grows over the prediction horizon. So we can see that as you go further and further over the horizon, the error in the forecast also grows until we get a new forecast, and then the process repeats itself. So now, based on this solar forecast and how we model the error.
Sorry for interruption. There are 2 minutes left.
All right. So based on this model that we have with the uncertainty, what we can do is we can obtain these tighter bounds, which will be a function of the distribution model that we choose for these forecast errors. And we can see that as we go into over the prediction horizon, the constraints become tighter and tighter till we get a new forecast. So based on this, now I can formulate my complete stochastic SOCP problem. So in the SOCP, I'm using relaxed power flow equations. I have the voltage constraints where I'm using the updated voltage bounds, which I get from the chance constraint. And then I have the battery model where I have constraints on the state of charge and the battery power limits. And then also I can, based on this solution that I get from the SOCP, I can solve a NLP, which I will warm start with the SOCP. Here I will use the actual nonlinear equations. Again, I have the same constraints on voltages with the updated bounds. And in this case, for the battery model, I fix the active power set point, so only have to care about the reactive power. So now this is the simulation setup that we had. We used a 1200 node ORU, Origin Rockland Radial Network from New York. We used a network reduction to make it a 131 node, which we will solve for a summer day around noon. The peak demand was 3.9 megawatt and the solar generation peak was 4.4 megawatt. So this is the simulation results that we get by comparing the results we get from the deterministic approach and the robust approach, where we take the uncertainty into account. So you can clearly see that the stochastic approach is able to manage significant uncertainty, and the results are feasible given the probability violation that we can choose. So finally, I show the comparison between the dispatch between the stochastic and deterministic. In figure 1, you can see that the battery dispatch is different. Furthermore, the reactive dispatch is negative in the stochastic formulation, which results in the voltages being within the bounds. Figure 3 shows the comparison between the losses, which are the objective function in this case. So clearly stochastic is a bit more conservative, which is expected. But if you see the total demand plus loss, then the difference is not that much, it's less than 4%. All right, so for future work, I want to study the trade-off between performance and security in chance constraint problems. Also want to study the effect of resource limitations on stochastic dispatch. Suppose that suppose, for example, if the reactive resource was limited, how would that affect our stochastic dispatch? Also want to improve the scalability of OPF so that when we go to larger and larger networks, we are still within the given time frame. And also want to validate representations of forecast error distributions, because the kind of forecast error distribution you choose affects your conservativeness of your solution. That's showing here between Gaussian and Chebyshev. I'd like to acknowledge my colleagues from the University of Vermont, Sanaduti Brahma and Pawan Rachela, and also Mike McGuire at ORU for helping us provide with the data. With that, I will conclude my presentation. If you have any questions, I'll be happy to answer. You can also check out our paper for further details. Thank you.
Thank you, Nawaf. Thank you. Very nice presentation. We have one question from Hussein. I don't know, I don't see the surname, it's just Hussein. Thanks for presentation. If SOCP relaxation fails to be exact, how can we rely on derived solution in terms of the active power injection?
So we're assuming that the SOCP will actually not be exact. Exact, I mean, you're saying that the duality gap is 0.
Yeah, I guess so.
Yeah, so we're assuming that that won't happen. That is why we are coupling it with an NLP. So what happens is that even if you don't get an exact solution from the SOCP, we warm start an NLP. And then from the NLP, we're guaranteed to get a feasible solution, an exact solution. It won't be the global optimum, but yeah, it will be feasible. But then we'll have a bound on the global optimality.
I see, I see.
Does that answer the question?
Yeah, we have another. Yeah, I don't know what Hussein should say, but yeah, I guess so. Dan has another question. Thank you, Nawaf, for your presentation. If I understood correctly, you are computing the safety margins to solve your stochastic formulation based on a linear sensitivity approach. Do you iterate on this to update the sensitivities with your new operating point?
Yeah, thanks, Dan. That's a very good question. So what we do is we're running this in a receding horizon a receding horizon way. So once we solve the NLP, we get the optimal point that we get from the NLP. We linearize based on that optimal point, and then we get the updated tighter bounds from that. So we don't iterate, we just use that operating point. The next time, in the next time step, when we again solve the NLP, then we will use that optimal solution to linearize. So we linearize after every time we solve SOCP and NLP coupled problem. So we don't iterate, but we use a different one every time we solve the deterministic problem.
Good, thank you. Nawaf, Sunset, it's my question now. You first solve your SOCP model, and then you find the solution. You linearize, maybe by, I don't know, Taylor series or whatever, and then you put it to your chance constraint model. Okay, it's fair, but just to be more, let's say, solving a tougher problem, why you don't put your chance constraint in the initial model, like reference 11?
Yeah, that's a very good point. So the thing is that because we are using a nonlinear model, putting a chance constraint formulation, like adding stochasticity on top of nonlinearity, really makes your problem
it's
very
SOCP,
very,
right? Still, we can solve chance constraint with the SOCP.
You would turn it into an SDP. So the thing was that we wanted to stay with an SOCP so that we could have a very fast solve time. So that was the reason that we thought that we'll separately have a separate problem for solving the chance constraint. Another added benefit is that we don't have to solve an optimization problem for chance constraint. That's just a simple linearization to get the tighter bounds. And so the only thing that we're solving is the deterministic problem. That's the only optimization we are solving.
Yeah. I don't see other question, but we have time for one more. So you're using Chebyshev, but unimodal Chebyshev, I guess you said. Well, it's less conservative, I agree, but let's say the confidence level is 99% or 99.5. Is it really less conservative than original Chebyshev or not? It's still very highly conservative.
Yeah, so it is less conservative than the original Chebyshev. So the original Chebyshev works for any distribution if you know the mean and the variance. So if I get any distribution within that mean and variance, I have guarantees with the Chebyshev. In the unimodal, we use the additional information that we have a unimodal distribution. So we are restricted to sort of less, there are less possibilities in the distribution. So
I totally agree, but if you go for confidence level of 99%, just 1% violation probability, is it much less conservative than original Chebyshev or no? I mean, maybe 98.
I didn't try it for like 99%, but I did try like regular for, I think in our case, we use 95%. And yeah, it is definitely much more conservative than unimodal.
Okay, very good, very good. Thank you so much, Nawaf. I personally, I really enjoyed. Thank you so much for very nice work. Thank you. Yeah, please stop sharing. Yeah. Well, now it's the time for our last speaker. Let me have a